Oh, hi. Hi. Yes, we've just had sorry, I realised I've had a bit of a mute moment there. Hi, my name's Brian Lawson. I'm the technical director. Thanks, Dan. Technical director for Projex Solutions Ltd. Um, we're a project management and engineering services company based in West Yorkshire. We do have an office up in Teesside as well. We're hosting these lectures in support of the Western area or the West Yorkshire area IMechE committees. A series of lectures have been run in collaboration with the University of Huddersfield. So thanks, Josh and Carl, for your inputs. This is the third of eight on the subject of steam trapping. The lectures are aired over Teams and presented by Dan Wells, who is the National Consultant Specialist for Spirax Sarco Limited. In a moment, I'll hand over to Dan. Just some basic logistics. The presentation will last approximately 50 minutes. There is an opportunity for Q&As at the end, but please post your questions using the chat function in Teams. So without further ado, over to you, Dan.
Great. Thank you very much for that introduction, Brian. And just to echo the thanks to both Projex, the IMechE, and also the University of Huddersfield for arranging and facilitating this series of presentations, series being the operative word there. We did present the first of the series of lectures back at the university in person 2 weeks ago on the topic of steam fundamentals, and it was great to see such a fantastic attendance. And then last week we presented a follow-up presentation on the topic of basic steam system design considerations. So today we're going to continue with the series, and we're going to look specifically at the topic of steam trapping itself. So with this being a series, I'm not going to dwell too much on the introduction to Spirax Sarco as a group of companies. Hopefully, those of you that have dialed in and attended the previous presentations will get an appreciation for the scale and place of the various subsidiary companies under the Spirax umbrella. But please do bear in mind that when we talk about steam systems, traditionally we've had to use gas in order to produce that steam, and therefore those nasty unwanted carbon emissions are a consequence. But please do bear in mind that under our electric thermal solutions division and those relatively new and emerging organisations that we've heavily invested in, we do have a suite of different innovations and technologies that can generate steam from grid or renewable energy. In other words, when we're working with a steam using client, we can help them to fully decarbonize yet retain their existing steam infrastructure. This is going to become more relevant in some of the future presentations in the series that we have planned. And of course, I've introduced that range of calculators, configurators, the resources in some detail. And I'd just like to come back to the point that one of the very, very most important things that we need to do when we're considering a steam system is calculate our client's cost of steam. If we understand our client's cost of steam, then any modifications, improvements, repairs, optimization that we configure will mean that we're able to demonstrate a payback, both in terms of financially, but also in terms of the reduced carbon emissions. So that's the very, very first question we want to ask our client. What's your cost of steam? 50% of the time, our client will have a good appreciation of what that is. 25% of the time, they may openly admit that they don't know and they need a little bit of assistance in calculating that true cost. But what's perhaps most worrying is around 25% of the time, our client will believe they understand their cost of steam, but they could be way off the mark because they could be calculating that cost of steam based on outdated information. For example, the cost of gas from 5 years ago, when, as we know, prior to the war in Ukraine, it was significantly cheaper. So it's important that we understand that cost of steam, because if we're able to make those repairs, those improvements, and generate a far, far better quality and condition of steam, boiler doesn't have to work as hard. We're not producing as much steam. We're not consuming as much gas. So our cost of energy, our cost of steam, and most importantly of all, those carbon emissions are going to be reduced. But we can only define that if we understand what the cost of steam is in the first place. So how do we calculate the cost of steam? We need to understand what the client's current cost of gas is, their cost of water, their cost of chemically conditioning that water, the pressure and therefore the temperature that the boiler will operate at, the combustion efficiency of the burner that furnishes the boiler, and most importantly of all, is the temperature of the water that goes into the boiler. If we know all of those variables, we've got a really, really good starting point for understanding what our client's current efficiency looks like. So the previous presentations we went through, the first presentation, the fundamentals, the relationships that steam has, and of course the importance of generating the best possible condition of steam in the boiler house. Remember, the drier the steam, the more energy, and therefore the greater the efficiency. But by having drier steam, it also means that we've minimized those erosion, corrosion, water hammer issues. And then last week, we looked at the steam design considerations. In other words, how we move the steam from the boiler house to get it to the various plant rooms and the various heat exchangers around site, so it arrives at its best possible condition, so we can keep a nice high efficiency, but also so we can minimize any mechanical or maintenance issues. So today we're going to move forward and we're going to consider what I believe personally to be the single most important component of the steam and condensate loop. It may not be the most interesting or the most exciting, but I believe it's the most important. Simply put, if we haven't selected the correct type of steam trap, if we haven't sized it correctly, if we haven't installed it correctly, and if we're not maintaining it, then we're never going to have a steam system that works safely, efficiently, producing a good condition of steam and minimizing any maintenance issues. So in today's presentation, I'm going to cover off quite a lot of information at quite a high level. So it's going to be quite a fast-paced presentation. If you do have any questions as we go, please drop them into the chat function and we'll revisit those when we're open for questions. And I can also make a PDF of the slide deck available that we're going through available upon request. So going back to the basic properties of steam, we know steam is a compressible gas. We know there's a relationship that steam has, that pressure temperature relationship, and we know that when steam gives up its heat energy, it condenses. When the steam condenses, it doesn't cool down. That means that liquid condensate will exist with exactly the same pressure temperature relationship that the steam has. We know that there's a very, very high density that steam has, and we know there's significantly less energy present within the condensate. We also know that steam moves in accordance with the pressure drop. So when we think about how the steam moves across a steam trap, for example, it means that we need a pressure within the steam infrastructure, the pipework itself, and the heat exchanger. That pressure needs to be higher than the pressure in the condensate line downstream of the steam trap. If we've got an equal pressure, or if the pressure in the condensate line is greater than the steam ahead of the steam trap, simply put, there's insufficient motive energy to move the condensate away. And that's when the condensate can back up and start to flood the heat exchanger, at which point we no longer have heat exchange, or the condensate can back up and flood the infrastructure, at which point we're more likely to experience erosion, corrosion, water hammer, and it also means the steam is more likely to deteriorate, get wetter and wetter, at which point there's less energy contained within the steam, and therefore the heat exchanger needs to call for a greater mass of steam. The boiler needs to work harder, and as such, our cost of gas, cost of steam, and our carbon emissions are going to increase. But fundamentally, we appreciate that when steam gives up its heat energy, it condenses. So we've got a phase change from a gas to a liquid. going to have the same density, the same mass. It just means that the condensate as a liquid has got a much, much smaller volume. And because the condensate's got less energy contained within it, we need to remove the condensate from the heat exchanger and from the steam trap, from the pipework itself. So that really explains the purpose of the steam trap. It's to get the condensate out of the infrastructure, but to retain the steam. So I'm not going to spend too much time on the steam tables because I did go through them in some detail in week 1 and week 2 of the series. But it really reminds us that by referring to the steam tables, we can understand all of those relationships. Pressure volume relationship, the pressure temperature relationship, the energy content of the steam. And of the total heat energy of the steam, we understand the latent heat energy, the useful heat energy that can pass across the thermal barrier and heat the process up. So when steam gives up its heat energy and condenses, we understand that the useful heat energy that's left behind, well, it's exactly the same as the energy that the water needs to contain before it boils. So it reminds us that when we're talking about the condensate in the pipework and the condensate in the heat exchanger, it's a byproduct. It's unwanted. It doesn't have any value whatsoever. But if we get that high temperature hot water away from the infrastructure and back to the boiler house, that's when that condensate does have a value, because it's going to help us generate that steam more rapidly and more efficiently. And of course, I've spoken about the temperature enthalpy curve, as this is really plotting the journey that water takes when we put it in the boiler and it boils off and evaporates to give us steam as a gas. So it really reminds us that when we're talking about the steam as it exists in the steam tables, this is assuming that that steam is 100% dry 100% of the time. And of course, we live in the real world where we know that the cyclic action of the boiler operation and the distribution pipework itself means that we can never guarantee that the steam gets to the heat exchanger sitting on that dry saturated steam line, which is representative of the values that we can see in the steam tables. The reality is the steam is going to exist in that wet steam zone at certain parts of the day. So as we've mentioned, wet steam is going to create a number of problems. First of all, we get the mechanical issues, the erosion, the corrosion, the water hammer. But also when we're talking about wet steam, we need to appreciate that that means we're likely to have a greater steam distribution loss. In other words, we get steam that condenses in the infrastructure. We might be putting 10,000 kilograms into the pipe. We won't be getting 10,000 kilograms out the other end. So we need those steam traps to drain that condensate away. And we also need the steam traps to ensure that, well, by draining the condensate away, we're preventing the steam from degrading and deteriorating as it moves around site. We want the steam to get to the heat exchanger at its driest, where we know we've got the maximum energy content that we can expect. So we've gone through those relationships as well. The pressure volume relationship and the pressure temperature relationship really reminds us two things. If we've got a steam trap that's, if it's failed in the fully open position, well, we could be distributing steam at 10 bar gauge. It's got a very, very small volume. And if that steam trap fails in the open position, the problem is that the infrastructure downstream of the steam trap, well, that's been designed to move a small volume, single phase fluid, condensate. Now, if that steam trap fails in the open position, we could potentially have high pressure, small volume steam that depressurizes. Because remember, we need that pressure drop across the steam trap. Otherwise, the condensate cannot move. But if we get high pressure steam depressurizing into a very, very small condensate infrastructure, we're going to get a huge amount of expansion. That can create a lot of damage into the infrastructure itself. The second problem is, because steam and condensate have got the same pressure temperature relationship, if we're assuming that that steam exists at 10 bar gauge, 184 degrees, the condensate is going to exist at the same pressure and at the same temperature, 184 degrees. So if that condensate depressurizes as it moves across a steam trap that's in the failed open position, a certain percentage, a certain mass of that condensate is going to boil off, it's going to change state from a single phase, non-compressible fluid, and it's going to expand considerably to a factor of around 1600 times. So if you can imagine that expansion taking place in the condensate infrastructure, you can appreciate that the damage it can pose. It's a significant health and safety risk. Simply put, we've got to vent that expansion away. And we do so by using one of those steam vents that we've spoken about in previous presentations. Now, those steam vents, think of them as a necessary evil. We've got to vent that expansion away. But whilst those steam vents are left unaddressed, we're losing a hell of a lot of energy. That boiler's racing to replace that missing steam. Our cost of steam, our cost of gas, and those carbon emissions are going to increase considerably. So keeping a visual eye out on those steam vents is probably one of the single most important things that we can do to ensure that we understand the overall efficiency of the wider steam trap population. So we also know that in certain critical applications, and this is a small number of applications by industry as a whole, I'm thinking in the food, beverage, pharmaceutical, in the hospital healthcare sector, then there are going to be certain applications where it's critically important that the condition of the steam is kept to a known dryness value, generally 95% or even better. So of course you can appreciate that the only way that we can really guarantee that we can hit that dryness value is by accurate and adequate steam trapping. That's very, very common in those critical applications that we've spoken about. And I'm going to cover that off in some further detail in one of the upcoming presentation series. Another thing we need to give thought to when we're talking about steam trapping is air venting. Now, we always talk about air venting at the same time as steam trapping, but we want to make sure that it's dealt with as an entirely separate issue altogether. The reason is some steam trap types are very, very good at venting air away and others are not. So we need to make sure that we've allowed for any air that's present within the steam system to be vented away. Two reasons, as we mentioned in the presentation last week. One is that air is the single biggest cause of corrosion in a steam system. And the second reason is if we're not venting the air away, we're going to have an insulating barrier to heat exchange. In other words, we've got an inefficiency. So we need to vent the air away using a thermostatic steam trap, never a mechanical steam trap. Never a mechanical air vent, beg your pardon, as we would commonly use on a water-based system. Because we know that air and water have got completely different densities, but of course, steam and air have got very, very similar densities, so it simply wouldn't work. But because there's a temperature difference between air and steam, then by having that thermostatic action, it means any air that's present will be pushed across that thermostatic element by the high pressure steam. And once the element sees that higher pressure, higher temperature steam, it will expand and lock the steam in. The thing to bear in mind is that air, because it's got a lesser density than steam, it wants to find its way to the high point, whereas, of course, condensate wants to find its way to the low point. So we're showing a typical heat exchanger here. When steam gives up its heat energy and condenses, that condensate, having a mass and a density, is going to fall to the bottom of the heat exchanger, which is logically where we want to place the steam trap. And as I've mentioned, some steam traps are very good at venting air and others are not. This is showing a float trap or a float thermostatic trap, which has got really good air venting properties. So when we're starting a steam heat exchanger up, first thing in the morning maybe, any air that's present together with any cold condensate is going to pass through the trap. So the float trap's an excellent choice. The problem is, once a lot of the condensate's drained away, the steam will push that bubble of air past the takeoff point. And without that little air vent at the top, we're going to have what we call air locking. That bubble of air means that we can't get the steam to see the entirety of the heat transfer surface area. So we're going to have uneven temperatures. We might get a little bit of product burn on or product spoilage. We're going to have an inefficiency, and it's also going to take longer and longer to get the heat exchanger up to temperature. So it's good practice to ensure that we can vent the air away from the low point within the steam trap at the same time as condensate removal, but as an entirely separate issue at the top of the heat exchanger, the opposite side to the steam inlet. So the next thing we need to give thought to is when we're talking about condensate, we know we need to get rid of it. The question is, where from? Where is that condensate going to exist? And simply put, the condensate exists wherever we've got heat loss. So that's going to occur in two different areas. We've got the condensate that's formed in the distribution pipework itself. Remember, we're going to be distributing steam at high pressures, high temperatures, maybe 10 bar gauge where it can exist at 184 degrees. And when steam gives up its heat energy, as a result of that large mass of metal in the distribution pipework, then we're going to get condensate. Yeah, that large infrastructure is essentially one big radiator. So we could be putting 10,000 kilograms of steam into the pipe. We need to know how much steam is going to condense and how much steam is likely to come out of the other end of the infrastructure 1,000 meters away. Well, we could calculate it, or we could apply a rule of thumb. That rule of thumb states that when we've got a reasonably good quality or condition of steam, we expect approximately 2%. In other words, in the case of generating 10,000 kilograms of steam, we expect about 200 kilograms of steam to condense out in the pipework itself. So we can use that information to size the steam traps. What capacity do they need to have? How many do we need? And how far apart do they need to be? That's what we call the running load. Now, it's important to understand that when we warm the infrastructure up at 9 o'clock on a Monday morning, or if we've isolated the run of steam to a building, for the first 15, 20 minutes or so, more and more of the steam is going to give up its energy to warm up the infrastructure. And therefore, the burden of condensate is going to be far, far greater. We call that the warming up load. So to calculate the warming up load, we're generally going to double the running load. So that 2%, 200 kilograms, it becomes 4%, 400 kilograms. But without taking into account that increased warming up load, those steam traps are undersized. That means the condensate is going to back up, it's going to slowly start to flood the infrastructure, and we're going to find that erosion, corrosion, water hammer creeping up on us slowly over time. We're going to find the steam slowly degrading and deteriorating. So the boiler's got to work harder, cost of steam, cost of gas, and the carbon emissions are going to increase. And then the rest of the steam, well, that's going to give up its heat energy at the heat exchanger, at the process. So if we know the duty of the heat exchanger, for example, it could be calling for 100 kilograms per hour of steam. We need to apply that same rule of thumb. We want to double, better still, triple that 100 kilograms of steam that is going to condense to size the steam trap. The reason being, we need to demonstrate that we can get that condensate away, including that higher warming up load, very, very quickly. Because if we're not getting the condensate away quickly, it's going to start to flood the heat exchanger. That's when we get a slowdown to the process. It's taking longer and longer to get the process to the appropriate temperature. So please do bear in mind that increased warming up load whenever we're sizing steam traps. So the steam traps themselves, there's no such thing as a universal steam trap. It'd make our life easier if there was. Spirax Sarco, we manufacture about 12,500 different types of steam traps, different sizes, capacities, operating principles, material construction, connections, flow configuration. Every steam trap needs to be uniquely selected in accordance with its application. But they all operate on 3 different operational principles, which I'm going to go through in the coming slides. The thing to bear in mind is we want to look at not just the application, not just the pressure, not just the mass of condensate. We need to look at everything else that could impact on the operation of the steam trap itself. Now, we know that processes change over time. Operating pressures and temperatures, the mass of steam required, the fabric of the building, it can change. So unless we've looked at the steam trap selection, it could well mean that we're moving to a position where we're replacing a steam trap every other week because it goes into failure. And the first thing that the mechanical or maintenance team do is they point the finger of blame to the trap manufacturer without appreciating that the trap selection may need revisiting and refining due to those changes. So those trap types, as I've mentioned, they operate on different principles of operation. One of the most popular types of trap is what we call the thermodynamic or the TD trap. This is ideally selected to remove the condensate that exists at high differential pressures. In other words, if we're distributing the steam at 10 bar gauge, then we've got a very, very small mass of condensate that needs to be pushed across that trap at a high pressure. This is an ideal candidate for that type of application. It's small, it's robust, it's easy to install. We can install it upside down and it'll still work as long as the direction of flows are correct. Common problems we get with this type of trap is because it operates in accordance with the pressure drop of that hot condensate. Whenever we get high temperature, high pressure condensate falling in pressure as it moves across the orifice, remember we get a very, very small mass of condensate boiling off, changing state to steam and expanding. That's what's operating that little floating disc there. And then when that very small mass of steam condenses, its collapsing volume sucks the disc closed. So that's the only moving part here. The problem is, if we've got a lot of air present within the steam, this type of trap can't tell the difference between steam and air. So it will lock shut because it thinks it's doing its job correctly. It's what we call air binding. And this is one of the reasons why we need to think about air venting as a completely separate topic, but at the same time as steam trapping. If the condensate were to be left in the pipework and freeze, well, it's not going to do any damage to the trap itself. As soon as the steam system's energized and that condensate warms up, it'll just defrost and carry on as normal. We also want to make sure that we're not lagging this type of trap, because if we lag it, then we're delaying the rate at which that steam is going to collapse and condense. In other words, we're reducing the capacity of the trap and the condensate could back up and start to flood the infrastructure. The next type of trap is what we call the thermostatic trap. And this works on the principle that the condensate's actually got to cool down a number of degrees before the steam trap will open. So we need a good run of unlagged pipework between the point where we're drawing the condensate away, whether it's the distribution pipework or the heat exchanger, and the trap itself. So once that condensate's cooled down by anywhere between 5 and 20 degrees, the trap will open, the steam pressure will push the condensate away. Once we get very, very high temperature condensate, that thermostatic capsule will expand and lock the condensate in the system until it's cooled down again. And you might think, well, what's the point in allowing the condensate to cool down? Aren't we losing energy? Well, in many applications, as we've mentioned, if we get a fall in condensate pressure, we're going to lose that energy by means of it boiling off and being lost to atmosphere up the vent. So by allowing the condensate to cool down, it actually means we're able to get a greater mass of high temperature hot condensate back to the boiler house. Another benefit of this type of trap It's always going to be in the open position whilst that condensate's cold. So it means that we can get a heat exchanger up to temperature very, very quickly. So it's very good if we've got a heat exchanger that's working with a lot of stops and starts. So think about like a still in the distillery, in the whiskey or the gin sectors, for example. We can get that cold condensate away, meaning we get a rapid warm-up time, and meaning we're minimizing the risk of any water hammer. It's also very good at venting air away because it works on that same thermostatic principle that the air vent works with. And then one of the most popular types of traps that we generally come across, especially the one up in the little top of the screen, this is what we call an FT, or float thermostatic traps. You've actually got two different steam traps that are in the same casting or the same body. The first, it works like your toilet cistern at home. So it works on the buoyancy principle. Condensate's got a greater density, and that's going to manipulate that little ball float. So once the condensate floods the trap, the float is going to open the valve. Steam pressure will push the condensate away. Once the condensate's gone, the ball float will close the trap. The second trap, it's that same little thermostatic element that we were talking about from the previous trap. So this means that the float trap's got a very, very good draining capacity because it's got two orifices essentially, and it's also very, very good at venting air. But remember, it's only going to vent air from the bottom of the heat exchanger. It doesn't take the place of a completely separate steam air vent that should be located at the top of the infrastructure. So this type of trap, the float trap, it's best suited to sit behind processors and heat exchangers that have got a low pressure because of the low temperature, but a greater mass. We can get the condensate away instantaneously, as opposed to using a TD trap that just spits the condensate out intermittently. And we're always going to have a mass of condensate that's held back so that valve doesn't open and close against a hard, dry mechanism. So that condensate acts as a little bit of a damper. But that means that if this trap were left outside for a prolonged period of time, we're susceptible to damage caused by freezing condensate. So if this trap is outside, we might want to give thought to a little bit of trace heating or lagging. So we know the implications of undersizing a trap. An undersized trap, we're not getting the condensate away. We're going to get more of those mechanical issues and more of those inefficiencies. But if we've got an oversized trap, then it's a cost that doesn't need to be there. More and more steam is going to condense as a result of the fabric of that ancillary. And it also means that the condensate is going to be pushed across a trap with a much, much greater velocity, which means we're more susceptible to mechanical issues like erosion. So once we've selected the appropriate type of trap, it's vitally important we give thought to how we need to size it correctly. So a couple of sizing examples I'm going to go through very quickly. On this example, we've got a process. We've got a steam coil that's heating a vessel of hot water, for example. Steam pressure, 4-bar gauge, and the pressure downstream of the steam trap, we're going to assume it's atmospheric or 0 bar. So the motive pressure within the steam, we express that differential pressure as being 4-bar gauge. So we've sized the coil so that we're consuming 200 kilograms of steam per hour. So we know that once the steam's given up its energy and condensed, we know that we need to remove 200 kilograms of steam per hour. So it tells us that that float trap's an excellent choice because it'll get rid of a large mass of steam as it produced very, very quickly. So every steam trap type's got its own sizing curve. The two pieces of information we need. First of all, it's that differential pressure, 4-bar gauge. That's plotted in the vertical line shown in red. And then we plot the mass of condensate we need to remove, 200 kilograms per hour. Remember, we need to double that running load to allow for that warming up load, that increased mass of condensate that's going to exist as soon as we energize that system. So you can see we've doubled the 200 to 400. So where the orange line intersects with the red line, that's how we size the appropriate steam trap. If we'd just sized the steam trap, taking into account that running load, it'd be significantly undersized. And that means we'd have problems with water hammer within the heat exchanger. The condensate will back up, and we'd have problems reaching the appropriate temperature in the appropriate time expected due to that flooding effect. So when we're sizing a TD trap, for example, with a very long run of pipe work, we may find from time to time that our client is managing the removal of the condensate using a dedicated TD or thermodynamic trap. In some cases, they may have a separate trap in parallel, which is what we call a fixed temperature discharge trap that's sometimes referred to as a dump valve. Simply put, when we've turned the steam system off, there's no pressure in the infrastructure, but there could still be a lot of condensate present. And if we leave that condensate over a prolonged period of time, we're more likely to experience problems with erosion, corrosion, water hammer, freezing, degrading steam. So that low temperature, low value condensate, it would be dumped to waste. There isn't a value to it, so there's no point bringing it back to the boiler house. We just dump it, hence the term dump valve. And then once the steam system's energized, that condensate escalates in temperature. When it gets to around 40, 45 degrees, that's when it does have a value because of its energy content. The thermostatic element in the dump valve would expand. It would lock the hot condensate in the infrastructure. That would back up in the dirt leg. And it's at that point that the hot condensate would then be managed by the steam trap and diverted back to the boiler house. So it really depends upon whether the client has or whether they've got expectations for that dump valve. You can see on this example here, we're looking at a steam distribution of 8,000 kilograms per hour, a steam pressure of 8 bar gauge, and again, we're assuming that there isn't any back pressure in the condensate line. So looking at that sizing example, 2% of 8,000 kilograms, that's 160 kilograms per hour. The green line plots that running load. Red line plots the differential pressure. Now, if our client, if they do have that dump valve will take care of that increased warming up load. But if they do not have a dump valve, then we need to double the capacity of the trap to allow for that increased warming up load. So the two selections really demonstrate that if we haven't taken into account that warming up load, we're in trouble because we know that the condensate is going to back up and start to flood the infrastructure. And that's when we're going to get those mechanical and efficiency issues. So other areas where we're going to want to install a steam trap, it's on the bottom of that separator that we spoke about last week. Any condensate that's removed from the steam system in order to keep it dry, it's going to condense as it passes across the separator. And we want to have a float trap to get rid of that massive condensate as soon as we can, without a risk of it backing up and flooding the infrastructure. Another steam trap ahead of control valves or isolating valves, because if those traps were to modulate closed or to isolate shut, it means we could be trapping the condensate. And then once that valve opens, we're at risk of that water hammer effect. And of course, at any low point in the infrastructure where that condensate could gravitate to. So when we're sizing the infrastructure, we need to make sure that now we've sized the trap correctly, we need to make sure that the pipework that's connecting the heat exchanger to the trap, we need to make sure that that's sized appropriately. Again, sizing in accordance with that increased warming up load. Because if we'd undersized that pipework, we're throttling it. It's going to back up and it's going to slowly back up into the heat exchanger. And that's when we're going to have those inefficiency issues. So the good news is when we're looking at the pipework between the trap and the heat exchanger, we won't have had a fall in pressure at this point. So providing we've taken into account that factor of 3 to take the warming up load into account, it means that we can size that pipework, assuming that it is a single phase non-compressible fluid. In other words, water pipe sizing charts suffice. But it's what happens downstream of the trap that catches a lot of people out. Remember, we need that pressure drop across the trap. We need motive pressure in the steam to be capable of pushing the condensate across the trap to a lower pressure. But that's when we get a certain amount of energy that needs to fall as the condensate falls in pressure. A certain amount of energy needs to be released. And that means that we're going to have to see a certain mass of condensate boil off and expand to a significant factor. And that expansion needs to be accounted for in the downstream infrastructure. So the charts over towards the right-hand side of the screen, they show us how we need to size the condensate pipework accordingly. It means that that expansion that takes place as a result of a known mass of condensate falling in pressure is going to result in a known factor of expansion. So if we were working with an installing contractor, for example, that had assumed that condensate was a single phase fluid, then essentially that pipework would be at risk of being significantly undersized. Nowhere for that expansion to go. That expansion results in condensate and the flash steam placing a back pressure on the steam trap, which means the condensate can now no longer exit the infrastructure or the heat exchanger. So every heat exchanger needs its own dedicated steam trap. We should never see something that we refer to as group trapping. And that's because very, very few heat exchange processes work in tandem, in unison. It's likely we're going to see different mass flow rates, different pressure drops, different expansion of the flash steam downstream of the trap. So if we got one process, it means that we could find that the flash steam expansion from one could result in a back pressurization and a delay to another process. Every single heat exchanger should have its own dedicated trap. And we'll come on and we'll discuss the condensate infrastructure behind the steam trap in a little bit more detail in 2 weeks' time. So we know what the risk of a trap that's failed in the open position is. Essentially, it's the financial impact. Because if that trap's failed, the boiler's racing to replace that missing steam. The cost of steam, the cost of gas, and those carbon emissions are really going to be the consequence. Again, reminding us why we want to keep a visual lookout for the operation of those vents. It tells us that there's one or more steam traps that have been left in the failed open position. So if we know the pressure of the steam system, I've got a relatively conservative pressure here of 6 bar gauge. Every steam trap type has got roughly the same size orifice for its BSP connection size. So if we know the steam pressure and the orifice size, we've got a really good understanding for how much steam is likely to be lost when that trap is in the failed open position. So if we think about a typical steam using site, it's by no means unusual for a steam using client to have anywhere between 400 and 600 steam traps on site. We generally work on a rule of thumb that says that with a well-designed, well-engineered steam system and a reasonably good maintenance regime and a reasonably good condition of steam, we'd expect a 1 in 10 failure rate. So we would expect anywhere between 40 and 60 steam traps to be in the failed open position over a period of 12 months. So taking that into account, if our client has calculated their cost of steam, again, 6 bar gauge is conservatively on the low side, £50 per tonne of steam, again, it's a very, very conservative figure, but it tells us that we can calculate what each individual steam trap is likely to represent in financial losses until such a time it can be replaced. Bearing in mind that could be anywhere between 40 and 60 steam traps that have been left failed. So that can be a significant financial and carbon inefficiency for our client to give thought to. So when a steam trap's failed in the closed position, then it's a little bit more difficult for us to understand the implications. We can't really calculate them financially. If it's behind a heat exchanger, we're not getting heat exchange. We're going to know about that very, very quickly because we can't warm the process up. But if it's a failed steam trap on the distribution pipework, that's when that condensate is going to back up and flood the infrastructure slowly over time. So those mechanical issues are really going to creep up on us. And we're going to find that the steam quality deteriorates, so it's got less energy in it, again, over time. So we wouldn't really notice it very, very quickly. And that really explains why so many of our steam using clients are going to have a manual audit, a steam trap survey undertaken periodically, generally once a year. It'd mean an engineer, first of all, locating and tagging each individual trap. Is it the correct type of trap for the application? Is it installed correctly? Is it failed in the open position or closed position? If it's failed open, what are the financial implications? What's the consequence in terms of the boiler working harder to consume more gas? What are the carbon emissions? What are the recommendations and observations? So that would generally be presented to the client, and we've really got to hope that they act on those recommendations as quickly as possible to reduce that inefficiency. But in the terms of many more sophisticated or critical processes, and especially for our clients that have got an appetite to move towards decarbonisation, then some form of instantaneous trap monitoring is going to provide a very, very attractive payback, because it means that those traps and those processes can be monitored and rectified instantaneously, even before they start to move towards the fully failed condition. And in many cases, they can even be monitored remotely by a third party, such as Projex or such as ourselves. So we've spoken about steam traps as individual components. The reality is a steam trap, it needs to be considered as a station, because we need a number of different ancillaries to ensure its safe operation and service requirements. So any number of isolation valves, strainers, check valves should be installed along with the steam trap itself. So when a client is moving towards what we call a traditional steam trapping station, we could have different materials of construction, multiple items to be screwed together. You've got a large footprint of space. An inexperienced installer could have these in the wrong configuration or in the wrong flow direction. So many clients choose to move towards what we call a modular, modern, efficient steam trapping station. So it brings together all of those components into one common casting. We've got a reduced footprint of space. It means the client they can change out and maintain those steam traps quickly and safely with a minimum of downtime. The trap itself, it doesn't matter what type of trap or what size of trap it is, it'll bolt onto the same ISO pad. So that means that we can change the trap type over the years if needs be. You've got a little check valve that's demonstrated here and a Y-type strainer to remove particulate. But it also means it's now more cost effective to install it with a small footprint of space in a much higher quality of material of construction, meaning that we've minimized the risk of any galvanic corrosion, and we've minimized the risk of any pinholing of any individual components. So again, I appreciate there's a lot of information to go through, and I've gone through that at a very, very high level. In short, please don't think of a steam trap as a common or universal device. It needs to be sized and selected in accordance with the application. If something changes over the years, then it's customary to review the steam trap and just make sure that everything it has now sized in accordance with whatever the changes are. Whenever we've got condensate moving across a steam trap, that fall in pressure will result in that flash steam expansion. And unless we've sized the pipework upstream and downstream of the trap, it can result in problems to the steam trap. In other words, the steam trap itself could be sized and selected correctly. It could be the broader infrastructure that needs a little bit of attention there. So once again, I'd like to thank you for your time. Next week, we're going to move forward from steam trapping, and we're going to look specifically at the topic of heat exchange or steam heat exchangers. So I do hope you can join us. And again, for those of you that are currently at university, please do take a moment to consider our Year in Industry programme and also our graduate programmes. The relevant pages on our website are now open, so it'd be great if you could express your interest, not just in steam engineering through our steam division, but also through our electric thermal solutions division and our fluid handling division. So once again, thank you so much for your attendance today. If you do wish to receive a PDF of the slide deck or a PDF attendance certificate, please do reach out to me, either email me directly or message me on LinkedIn, and I'd be delighted to make that happen. So Brian, I don't know if we've had any questions that have arrived in the chat function, but I'd be happy to go through anything.
Okay, thanks Dan, as usual, top-notch presentation. Nothing come through question-wise, so I enjoyed the lecture again this week. Steam trapping, air and condensate, two sides of a quality and a health and safety challenge. And how you described that thermodynamic trap as being small and dynamic. I thought for a moment you were talking about me, but that's the end of my malarkey for this evening. There doesn't seem to be any questions come in, so I just thank you again, Dan, and thanks to the IMechE Western Area Committee, the University of Huddersfield, and the guys at Projex Solutions in the back office. Just a reminder that the next lecture will be on the subject of heat exchange, and it's on the 8th of October. That's same time next week. So thanks so much, Dan, and thanks everybody for making contact.
Brian, would I be right in saying that these are going to be available on YouTube in the coming weeks?
Yeah, that's. I'm pretty sure that's our plan. I'll check back in the office. We're keeping a record of them, so we've got them recorded, and I'm pretty sure we'll be able to find a way of getting them on YouTube, because Projex Solutions have got a YouTube channel, and I know the IMechE's got something that I'm sure we'll be able to leverage. So the short answer, yes.
Perfect. Well, I look forward to presenting to you all same time next week.
Okay. I did add a question. I don't know if you can read it or not.
Yeah, fire away. Yeah, we've got a couple of minutes.
Yep.
I just wrote it in the chat. So I just wanted to ask, is condensate always present in steam? Number one, is it in liquid form but still hot? And is it reducing the steam quality and temperature, and that's why we want to remove it? So basically, all steam traps are basically a condensate trap. Is that correct?
Yes, correct. A steam trap, you can call it a steam trap, you can call it a condensate trap. The purpose of the steam trap is to allow the condensate to drain away, either from the pipework or from the heat exchanger, but to lock the steam in. Is there always going to be condensate? Yes. Whenever the steam is going to give up its heat energy, we will have condensate. So steam is 90 to 95% of the time, it's used for warming something up. So wherever we've got heat loss, for example, at a heat exchanger, the steam is going to give up its energy. And when the steam gives up its heat energy, condensate is the byproduct. We need to drain that condensate away. Condensate is also going to exist in the pipework. It's unavoidable, because that pipework, the mass of steel, it's one big radiator. We are going to have heat loss. Again, it's unavoidable. So the purpose of the steam trap is to allow the condensate to drain away, because it doesn't have enough energy present within it. It's hot water, but it doesn't have enough energy in it. So unless we're getting that
liquid form, the condensate.
It's in liquid form when it's under pressure. So When it's at a stable pressure, it is in liquid form. But we need that pressure drop across the steam trap. We need the steam pressure to be able to push the condensate out of the infrastructure. So we need a lower pressure downstream of the steam trap. So what happens is if we've got condensate under pressure at 10 bar gauge, 184 degrees, if that condensate falls to atmospheric, we know that that condensate cannot exist as hot water at 0 bar gauge. A certain mass or a certain percentage of that hot condensate, as it depressurizes, it's going to boil off. It's going to change back to steam again. So it's at that point we get a biphase. We get the liquid condensate at 100 degrees or thereabouts, but we also get that huge expansion of the steam that's boiled off. So the short answer is condensate, yes, it is a liquid at a stable pressure. Whenever there's a fall in pressure, it will be a biphase.
Okay. And the best piping material for steam is it always stainless steel, or people use carbon steel as well?
No.
Okay.
Depends on the application. Shed 40 is Shed 40 or Shed 80 is perfectly acceptable for plant steam systems. When we're moving towards more critical steam systems, like for food, beverage, pharmaceutical, you'd want to move towards 316 because we don't want there to be any contamination from corrosion and rust present within the steam.
Thanks very much, Dan. Good answer.
Thank you.
Great.
Okay,
well, thank you again. If there are any further questions, I'm happy to take them up offline on LinkedIn.
Okay, that's brilliant, Dan, and thanks everybody for connecting in. Talk to you next week.
Thank you.
Bye.
Thank you.
Goodbye.
Bye.
Thank you very much.